Introduction. The intellectual project initiated in the year 2018, catalyzed by Giuseppe Paesi's discovery of Ceres, represents a pivotal moment in celestial mechanics and observational astronomy. It is within this specific, energized context that the work represented by Karl Ludwig Harding's discovery of Juno finds its profound significance. To evaluate this achievement, one must apprehend it as an integral part of a multi-year, pan-European endeavor, a scientific work whose narrative begins with a search for a missing planet and culminates in the confirmation of a new class of celestial bodies. The very titling of this investigation, and Karl Ludwig Harding, the discovery of Juno, frames Harding's specific contribution as a fulfillment and complication of the questions posed by the initial breakthrough. This essay will conduct a rigorous evaluation of the claims, methodologies, and implications inherent in Harding's discovery, proceeding through the logical stages of the scientific process he undertook. It will analyze the conceptual foundation underpinning his search, the empirical act of detection, the mathematical confirmation of the object's nature, its subsequent physical characterization, and its ultimate contribution to the theoretical debates of its time. Treating each phase as a distinct section of a composite scientific work, the analysis will demonstrate that Harding's contribution was a masterpiece of systematic diligence, which both validated the new collaborative model of astronomical research and fundamentally enriched the emerging understanding of the solar system's architecture. Section 1. The conceptual and methodological framework of the search, the foundational claim of the entire enterprise, preceding Harding's direct involvement, was the proposition of a predictable order in the solar system, famously articulated in the Titius-Bode formulation. This empirical relationship, which proposed a mathematical progression for the distances of planets from the Sun, contained a conspicuous vacancy between the orbits of Mars and Jupiter. The validity of this formulation, as a predictive tool, became the central implicit argument driving the search. Following the successful discovery of Uranus by William Herschel at a distance that corresponded with the pattern, the framework gained immense credibility among European astronomers. This led to the formation in 1800 of the Vereinigte Astronomische Gesellschaft, a collective of 24 observers popularly known as the Celestial Police, organized by Baron Franz Xaver von Zach. This group represented a new methodology, in itself a coordinated, systematic, and distributed search effort designed to survey the zodiac for predicted planet. Harding, working at the Lilienthal Observatory under the patronage of Johann Hieronymus Schröter, was a prominent member of this society. The underlying claim of this organization was that discovery could be industrialized, partitioned, and pursued with collective efficiency, moving beyond the serendipity that had characterized many previous findings. Harding's work, therefore, was predicated on the acceptance of two primary claims: the astronomical claim of a missing planet at a specific distance, and the methodological claim that a collaborative, systematic survey was the optimal means to find it. His own research was an application and a test of this framework, with his assigned section of the zodiac becoming the canvas for his meticulous labour. The intellectual ground was thus thoroughly prepared, making his eventual discovery an expected, albeit brilliant, outcome of a pre-existing and highly structured scientific program. Section 2. The core observational claim and the evidence of detection. The central and most direct claim of Harding's work was the identification of a new, nobile celestial object within the constellation Pisces on the 1st of September, 1804. This claim rested entirely on the evidence of meticulous, repetitive observation and the rigorous practice of comparative celestial cartography. Harding was at the time deeply engaged in the preparation of his own stellar atlas, the Atlas Novus Celestis. This project required him to systematically chart all stars down to a faint magnitude, an undertaking that cultivated an unparalleled familiarity with his assigned fields of view. The methodology was one of patient, accretive data collection. The discovery itself was precipitated by the appearance of a faint, 8th magnitude stellar point, absent from his own and prior charts of the region. The critical evidence supporting his claim of discovery was its motion. Upon re-observing the position of this new star over subsequent nights, he confirmed its displacement relative to the fixed background stars. His recorded measurements of right ascension and declination on September 3rd and 4th provided the irrefutable dataset demonstrating that the object was a member of the solar system rather than a distant star. This act of detection was a triumph of the systematic approach advocated by the Celestial Police. It was a direct consequence of a planned search, executed with superior instrumentation at the Lilienthal Observatory, which housed one of Europe's most powerful reflecting telescopes. The claim was simple: an object previously unknown exists at these coordinates and exhibits planetary motion. The evidence was a table of changing positions. This specificity and the reproducibility of the observation formed an unassailable foundation for all subsequent analysis, immediately communicated to the astronomical community through von Zach's journal, the Monatlich Correspondence, which served as the official organ for the verification and dissemination of such findings. Section 3. The argument for planetary status through orbital determination. Following the initial detection, the next crucial claim involved the object's physical identity. The immediate question was whether it was a comet or the sought-after planet. Resolving this required a determination of its orbit. The primary argument for its planetary status would come from the calculation of a closed, elliptical path confined largely to the region between Mars and Jupiter. For this, Harding and the wider astronomical community relied upon the formidable analytical engine of Carl Friedrich Gauss. Gauss had, following the discovery of series in 1801, developed a revolutionary new method for calculating an orbit from only a few observations. This technique, based on the method of least squares, was an immense methodological leap forward, allowing for rapid and accurate orbital solutions. Harding supplied his precise observational data to Gauss, who then applied his computational framework. The resulting claim was that the new body, which Harding proposed to name Juno, moved in a stable, elliptical orbit around the Sun. The specific parameters of this orbit constituted the detailed evidence. Gauss calculated a semi-major axis of approximately 2.67 astronomical units, placing it squarely in the gap predicted by the Tishus-Bode formulation. Its orbital period was calculated to be around 4.36 years. These figures were quintessentially planetary. They described an object permanently bound to the solar system, moving in a predictable path wholly unlike the highly elongated, near-parabolic trajectories of most known comets. The successful application of Gauss' method and the resulting orbital elements served as the conclusive argument transforming Harding's moving star into a new member of the planetary family. The claim was longer: I see an object move, but this object moves according to these specific orbital laws, confirming its planetary nature. Section 4. The physical characterization and nominal solidification. With Juno's planetary status secured through mathematics, the subsequent set of claims concerned its physical nature and its place within the celestial nomenclature. Observationally, Harding and others noted that Juno was substantially fainter than Ceres or the second such body, Pallas, discovered by Heinrich Olbers in 1802. This faintness, given its orbital distance, implied a smaller physical size. Here, the work entered a domain of inference, where the claim of its diminutive stature was based on the principles of photometry. The evidence was its apparent magnitude, which even at opposition remained faint. This gave rise to the developing characterization of these new bodies as being a different order of object from traditional planets like Mars or Jupiter. William Herschel had already proposed the term asteroid for Ceres, and the discovery of a third, even smaller body, reinforced his argument for a new classification. Harding's own contribution to this discourse was both observational and nominal. By proposing the name Juno, he followed the classical mythological precedent set by Ceres and Pallas. This act was a subtle but powerful claim for the object's significance. Choosing the name of the queen of the Roman gods, the sister and wife of Juno, was a deliberate placement of the new body into the highest echelon of the celestial pantheon. This nominal act worked in concert with the orbital data to cement its identity. It was a strategic choice, had simultaneously affirmed its planetary status in the classical tradition while its observed faintness and small size contributed to the growing body of evidence that these were, in fact, members of a new and populous category of solar system inhabitant, a claim that complicated the very definition of the word plan. Section 5. The theoretical implications of Juno's orbital peculiarities. The final and perhaps most profound area of evaluation concerns how the specific claims about Juno's orbit influenced the dominant cosmological theories of the period. Heinrich Olbers, following his discovery of Pallas, had posited a dramatic hypothesis that Ceres and Pallas were fragments of a much larger, single planet that had been destroyed in a cataclysmic event. The primary evidence for this claim was that the orbits of Ceres and Pallas nearly intersected at 2 points, suggesting a common point of origin. Harding's discovery of Juno provided a critical new test case for this theory. The data from Gauss calculations yielded an orbit for Juno that was peculiar, even when compared to the other asteroids. Its eccentricity, with a value of approximately 0.257, was extreme, higher than that of any known planet and describing a markedly elongated ellipse. More startling was its orbital inclination. Juno's path was tilted at an angle of 13 degrees with respect to the ecliptic plane, the common plane of the solar system's planets. This high inclination was a significant anomaly. The claim that emerged from this data was that Juno's orbit was entirely consistent with, and indeed strongly supportive of, Olbers' exploded planet hypothesis. An explosive dispersal would naturally result in fragments being cast into orbits of high eccentricity and high inclination, deviating significantly from the relatively flat, circular paths of the major planets. Juno's orbit, therefore, became a powerful piece of evidence in an ongoing scientific debate. It transformed Olbers' idea from a clever speculation into a robust theory with accumulating, predictive power. Harding's work, in this sense, did more than add a new object to the solar inventory. It provided the crucial third data point that solidified a compelling narrative about the history and dynamism of the solar system, suggesting a past far more violent and chaotic than the clockwork universe envisioned by earlier generations. The discovery's claim was that the solar system's architecture was more complex and its history more dramatic than previously. Under's conclusion the Instandatenbenin project, culminating in Karl Ludwig Harding's Instandatenbenin discovery of Juno, stands as a testament to a shift in scientific practice and a deepening of cosmic perspective. A section-by-section evaluation of the work reveals a chain of claims, each built upon the last with unimpeachable logic and empirical rigor. The initial framework, resting on the Titius-Bode formulation and the collaborative methodology of the Celestial Police, established the conditions for success. Harding's core claim, the detection of a mobile object, was a triumph of systematic observation and cartographic diligence. This was then elevated by the analytical power of Gaussian mathematics, which translated positional data into a definitive claim of planetary status through a specific, calculated orbit. The subsequent characterization of Juno as small and faint, coupled with its regal naming, simultaneously embedded it within classical tradition and the emerging category of asteroids. Ultimately, the peculiar parameters of its orbit provided powerful, corroborating evidence for Olbers' disruptive planet hypothesis, fundamentally altering the prevailing conception of the solar system's stability and history. Harding's discovery was therefore a complex intellectual achievement. It was an act of confirmation, validating a predictive model and a new collaborative research method. It was an act of complication, adding a new type of object that blurred the definition of a planet. And it was an act of theoretical reinforcement, providing the critical data that lent profound credibility to a new and dramatic cosmological narrative. The work's enduring significance lies in its perfect illustration of early 19th century astronomy in action, a synthesis of empirical patience, mathematical genius, and theoretical audacity that collectively expanded the known universe and the methods by which it could be understood.